to listen, okay? Because I don't mind giving you guys the molecule kits to play with, but make sure you don't get too distracted by them. Today's topic, at least for number 2, is explaining molecular formulas. We're going to focus very specifically today on molecular bonds. I'm going to do a quick recap from yesterday. Yesterday I introduced a new term to you guys. It's called electronegativity. You guys remember what electronegativity is? In general, broad terms? Yeah, it's basically about how much an element wanting electrons. Why would an element want electrons in the first place? Well, yeah, but like, why do the electrons stay? Why don't they just leave and go wherever they want? Nucleus. Nucleuses are positive, right? And electrons are negative. So the nucleus, in general, has a general affinity and attraction for electrons. However, each one is a little bit different. Some nuclei are really large. The valence electrons are really, really far away. And the further away they get, the less they want to stay. And so there's a lot of different factors in play. So Linus Pauling came up with this electronegativity scale. I can't remember what the date was, but the whole point is that it's on a scale from 0 to 4. If you have a ranking of 4, which is fluorine, it has the most affinity for electrons. It wants electrons a lot. And you can work your way all the way down from 4 all the way down to essentially 0, which those are things where they don't want electrons. Well, like, say, sodium, I believe, is like a 0.9 on the scale. So, sodium, I guess, would like electrons, but only if you can give it 7. Does that make sense? Sodium has 1 valence electron. It's way more likely to get rid of its 1, but I guess in theory it could pick up 7. It's not very likely, but you know what I'm saying here? Okay. So what we can do then is we can rank all of our bonds then on like a continuum, on a spectrum. Just like you do like in, I don't know, social studies where you do like political spectrums or something, only this is way more exciting. No, it's not actually. Over here, what we've got is a scenario where if the electronegativity difference is high, you get what you guys now previously knew as ionic bonds. Okay? So that would be, for an example, that would be Na and Cl. I believe chlorine was like 3.2, sodium 0.9. In this fight for electrons, who wants the electrons more? Well, chlorine. So much so that chlorine is literally going to steal. It's like taking candy from a baby. They are literally taking those electrons away and saying, gimme. Does that make sense? But as we work our way across the continuum over here, we get to a spot where the electronegativity difference is low. Like, for example, in H2O. Now, H2O isn't super, super low. We can even go lower than this. But in H2O, we have hydrogen at 2.6, I believe, and oxygen at 3.4. It's been a while. I don't have them all memorized perfectly. But in this case right here, although there's a clear winner in the fight, it's still more of a sharing scenario. And so you have as an unequal sharing. And I showed you guys a picture last day of how we try to represent these bonds. If I were to have, like, say, like an overlap section here, where here's a nucleus, here's another nucleus, here's your electrons as you go around there. Sometimes we put some electrons in this shared grouping area, right? This is a nucleus of positives. This is a nucleus of positives. Electrons around. In this middle section here where they are sharing their electrons, sometimes it's not even sharing. Sometimes it's like my analogy, it's like Kinsey and Cameron sharing. When Kinsey and Cami share, it really means Kinsey gets it like 80% of the time and Cami gets it 20%. But Cami's 3, she doesn't really care and notice. You know what I'm saying here? Well, in that scenario here, it leads to what we're going to talk about eventually, which is called polar molecules. And those polar molecules then have slight discrepancies between them that allows them to stick together. This hell explains why water is actually in a liquid state. Sodium chloride's in a solid state, because that's salt, right? Salt is solid. Water is in a liquid state. It's also possible for us to have a molecule like, say, nitrogen gas. The way nitrogen gas works is that nitrogen is literally bonding to itself. Okay? Now, if you were to have a fight between nitrogen and another nitrogen, I don't remember what its electronegativity is, so I'm just going to make it up and say it's 3.0. Who wins in a fight between two identical nitrogens? Nobody. No. Unlike in the hydrogen-oxygen fight, where there's a slight winner here, this is where in this fight for electrons, where they have shared electrons in this middle section right here, it's an exact tie. And I'm going to show you guys later as we build on that this actually leads to a spot where there is actually no electronegativity difference. And that can actually cause things to form gases when you're done. So that's ultimately my goal, is to use electronegativities and to explain to you, one, internally, how do molecules stay together? And two, once we internally have made a molecule, what causes it to be attracted to other molecules? Because honestly, otherwise, if everything in the universe was made out of a gas, we would have really not a whole lot of diversity of matter. You know what I'm saying here? Like, we couldn't exist if it wasn't for solids, liquids, and gases all existing. So that's what I'm building towards. So, wait, a little bit more review from what we did last day then. Dot diagrams are a great way to start. You guys are obviously playing with the little molecule kits, but if we don't have one of those in front of us, one of the best ways to do this is to draw a dot diagram and then piece it together like, say, Lego blocks. We did water the other day, where all you're looking to do is draw some hydrogens, draw an oxygen that looks like, say, this, and then you piece these ones together, and the link between here, this is a bond. Hopefully one of the things I can impress on you guys today is that as you play around with these things here, however your molecule kits work, I really don't care, but this is meant to represent a nucleus of an atom, and this right here, the stick kind of idea, is really meant to represent electrons, a bond of electrons. But that's one of the things, is that these electrons, they don't exist in like a stick format at all. They actually exist in maybe something that more looks like this. We often use one of these to illustrate orbitals, which means that somewhere inside of here, there are 2 electrons. I don't know where they are. As soon as I look for the electrons, they're already gone. Okay. One of the other problems with this here is that those electrons, they're so small that they're very hard to detect. When we are able to detect them, though, one of the things that scientists have noticed, this is a physics thing again, is that one of the electrons always spins clockwise, and the other one always spins counterclockwise. And that leads to that quantum entanglement thing, if you know anything about quantum physics, which is super cool and super, like, so far beyond my head anyways. Like, it's cool stuff. So, okay, let's go do a task here. Can you guys find this page here? We're going to try to draw some Lewis structures. So you have to put the molecules away for just a minute. Don't worry, I'll let you play more later. So here's what we're aiming to do. I need to help you guys build up to being able to do something like this. NH3 is ammonia. Eventually, when we do our lab, you guys are going to go to this program, you're going to type in ammonia, and it's going to show you a molecule. Now, you guys know the formula for NH3, right? It's 1 nitrogen and 3 hydrogens. And as you look at this molecule right here, the blue one's got to be the nitrogen, right? And the white ones have got to be the hydrogens. What I want to eventually get to, though, is what does it look like in 3 dimensions? Because if you play around with this guy right here, you might notice that it's actually not perfectly flat. You guys see that? It's more like a tripod. And so, first thing we're going to do is learn how to draw these things like in 2 dimensions on flat paper. And then we're going to work up our way to trying to either draw them or model them in 3 dimensions. And then hopefully with our understanding of 3 dimensions, we can then explain why ammonia is a liquid, not a solid or a gas. Okay, so for one of these ones right here, if you want to do a Lewis structure, you use those Lewis dot diagrams. So I would recommend start by drawing something like this. We need a nitrogen, and we need 3 hydrogens. Oh, that's 4 hydrogens. And then start putting the dots around them appropriately. So how many valence electrons does a nitrogen have? Lithium, beryllium, boron, carbon, nitrogen. Can you guys count the way I did there? 5. Okay. But we have to put them in the right pairs here. You don't go like this. 1, 2, 3, 4, 5. That's not correct. Basically, the way they work is that these electrons, they want to spread out as much as they can. So this side, this side, this side, and this side each take 1 valence electron. And then eventually, I use the analogy of like, let's say you're driving on the school bus, and there's only like, say, 5 seats, and there's only 4 of you on the bus. Wouldn't you each take your own seat and spread out evenly? But what would happen if eventually more kids get on the bus? Eventually, someone's got to bunk up and share and sit next to somebody else, right? You know what I'm saying here? That same sort of analogy happens here. I've gone 1, 2, 3, 4. Everybody's spread out in the 4 available orbitals. Now the 5th person comes on the bus. I don't care who it is, but somebody's got to share. Okay. And then hydrogen goes like this, this, and this, because they all have 1. You guys can probably figure out how this is going to piece together. What's going to end up happening is, let's see, can I lift this one? I'm going to bring this one over here like that. I'm going to bring this one over there like that. And I'm going to bring this one up here like that. And there, now I've drawn the Lewis structure for ammonia. Does that make sense? It literally is just as simple as like draw all the Lego pieces out and then just like fit them together. Okay. Rebecca, you asked me earlier whether like that molecule would be like valid that you drew. It would be valid so long as if we were to look at it from this point of view, maybe not the 3D point of view, but as long as everybody has a filled valence shell to either 2 or 8 electrons, then it's logical. I mean, it still may not occur, but at least it's plausible. Hydrogen has 2 electrons. Hydrogen has 2 electrons. Hydrogen has 2 electrons. And this nitrogen has access to 8. Does that make sense? If I were to draw circles here, this nitrogen has 8 in its circle. This hydrogen has 2. This hydrogen has 2. This hydrogen has 2. This section right here that I'm highlighting in, that would be like those little sticky pieces that you're using right now when you make it. Those 2 sticky pieces are really a way to represent a sharing of mutually sharing electrons. It may not be equal sharing, but at least there's like an overlap of them. Any questions on that one? Let's try another one. Let's try to draw the Lewis structure for water. We already did this one earlier, but let's do it again. So water is H2O. Well, in terms of water being H2O, we need 2 hydrogens. So there's 1, there's 2. We need an oxygen. Oxygen needs 6 valence electrons. So I drew 6 around like this. Really, if I were doing it a little bit slower, you'd go 1, 2, 3, 4, and then for the remaining 2, somebody's got to share. I don't really care which ones share, whether it's like 2 side by side. Thank you. Or across from each other. It really doesn't matter. And then the last thing you do is you try to piece it together. So take this hydrogen and make it go, say, right here. Take this hydrogen, make it go right there, and now you've got water. That makes sense? So there's a Lewis structure for water. Here's one of the issues with the Lewis structure, though. When you're drawing these in 2 dimensions, it doesn't account for the fact that in 3 dimensions, sometimes things have a little bit of a different shape to them. If I were to type in water, this is what water looks like. And some of you have already maybe made a water molecule because you have one right there too. One of the issues then is that if you try to make yourself a water molecule, here's a hydrogen, but why is there nothing down here in this section? Well, I'd like to actually show you that right now if you have some molecules in front of you. If you have one that looks like, say, one of these guys here that goes out in 4 directions, if you have one like this, it's a very common shape. We call it a tetrahedral. And I got notes on it later, but it basically goes in 1, 2, 3, 4 directions. Can you guys kind of visualize that? The basic idea is that don't electrons want to spread out as much as they possibly can? Because aren't electrons all negative? Shouldn't these electrons right here want to repel these electrons as much as possible? So it wouldn't really make sense to have a molecule where all of the bonds are like all right together like that. Like why would all the electrons clump together like this? Wouldn't the electrons, just like students on a bus, want to spread out? So you guys would go there, you guys would go there, you guys would go here. Here's the problem with how water works then. I want to go back a slide. When I draw this water molecule, I need to create a bond to, say, hydrogen. So give me a sec while I get some hydrogens going here. So let's say that this little white ball I just made there, that's my hydrogen. And here is my other hydrogen. Can you guys start to see now why it has to have a bit of a V, a bend shape to it when you put it in 3 dimensions? Although right here, it looks like it's flat across, one of the issues is that right here and right here at the top and the bottom, we have a grouping of 2 electrons. Do you guys remember from yesterday what we call a grouping of 2 electrons that's not in a bond? It's called a lone pair. And so we would often use something like these things right here, if your model kit has them, to represent a lone pair. So this is what water actually looks like in 3 dimensions. What you've got is 4 directions. One direction takes the hydrogens. That could be, like, say, this one right here. Another direction also takes the hydrogen. That's this direction right here. But in the other 2 orbitals, there's got to be room for electrons to go around. And so what ends up happening is water, when you ignore the electrons, has a bit of a V shape to it. That's one of the downsides to these Lewis dot diagrams, though, is that because they're being drawn in just flat paper in 2 dimensions, you don't really get a sense for what their shape is. So eventually I want to get to that, though, and show you how we can figure out these shapes in 3D. Okay, a little bit of terminology I need you guys to know. We were just drawing Lewis dot diagrams. If I ask you, sorry, choking on my candy. If I ask you for what's called a structural formula, the most common way of drawing a structural formula, all you do is you take the 2 electrons, and rather than drawing 2 dots here, you replace it with a line. So you've ever seen a picture like this? This is methanol in Lewis structure. This is methanol in Kekulé structural formula. It's literally the exact same thing, only. No, there should only be one proper way of drawing it still. I guess what you could do though is you could go like H to O to C to H to H to H, if that's what you're saying. Like I could reverse it and have it go backwards. I could draw it like H to O to C to H to H to H. But like the order is still consistent, if that makes sense. The only difference though is rather than drawing dots, replace all the dots with lines. Okay. Sometimes what we then do is occasionally we will put those lone pairs on top of oxygen. Sometimes we don't. It really depends on how lazy a person is choosing to be. That's really what it comes down to. What you should then have, though, is everything should still fit either the octet rule, or if it's hydrogen, like a 2 electron rule. So like this carbon right here, does this carbon still have 8 electrons around it? Yeah, 2, 4, 6, 8. Does this oxygen right here still have 8 electrons around it? Yeah, 2, 4, 6, 8. So that's the only difference. If I ever ask you for a Kekulé structural formula, just replace all of the dots with lines. But why did I not put like a line right here and right here? Because that wasn't a bond. Okay, I need to make sure you get the difference between the two. 2 electrons just sitting there by themselves, we call those a lone pair. Whereas 2 electrons being in the shared space between things, that's what a bond is. So that's why this one right here and this one right here shouldn't have been written as a bond. So I've got some pictures here, just some generic formulas. You guys are going to see more and more of these as we go along. If you guys can kind of like see a few of these, let's just look through, say, this one here as an example. Does everybody fit the octet rule? Yeah, I think so, right? This hydrogen has 2 electrons, because the 2 electrons are what a bond is, right? This sulfur right here has 1, 2, 3, 4, 5, 6, 7, 8. Sulfur fits. This carbon right here has 1, 2, 3, 4, 5, 6, 7, 8. Okay. Well, let's go over here to say this guy right here. What's happening with this carbon here instead? Does it still fit the octet rule? Yeah, it's still got 1, 2, 3, 4, but look how there's 2 lines right here. This is called a double bond. I want to show you how to make one of those in your molecule kits. A double bond looks something like this. If you have the right kind of kit, I get these little curved ones. And what ends up happening, here, let's fill it out there, is that, you know how there's like maybe 4 slots off of your molecule to put all the different sides on there? What ends up happening is 2 electrons go this way, 2 electrons go this way, but then like this slot and this slot, they both have like a curvy line there. Now keep in mind, that's not actually what it looks like. If you ever have a double bond, all it means is that inside this generic area right here, there's 4 electrons, that's all. So if you have the right ones there, you're probably looking for like the longer ones that are flexy and bendy. Yeah, then you can actually put together like a double bond. And that occurs too. So I'll show you some more of those over our next slides. Okay, let's try one more here. You guys do this without me. Try to draw the structural formula for methane. So try beating me to this one here. Draw me what methane looks like in a structural formula. Here's what you're going to do then. Draw it with all the dots, like we just did a few minutes ago, and then after that, then just remove all the dots and put lines instead. And after a while, this gets actually quite, you get pretty fast at this after a while. So hopefully you're along this path here. Here's a carbon. It's got 4, what do we call these single electrons again? Bonding electron. It's a common thought because you think they're by themselves, so you want to call them lone, right? But lone pair refers to a group of electrons, 2 entangled electrons, that are forever and now alone. They're not going to ever form a bond. So those are bonding electrons, and then here's 4 hydrogens. And I mean, I don't mean to be rude here, but I feel like my 5-year-old who's really good at Legos could probably fit this together if I taught her the rules, right? Like, okay, pick this one up, or I guess they're all in a group now. Never mind. You guys get the idea, though, right? One of the hydrogens goes here, one goes there, one goes there, one goes there. There. Now, that would have been a Lewis dot diagram. So a Kekule structural diagram would look like this. Carbon to hydrogen to hydrogen to hydrogen in 4 different directions. Now, again, I want to eventually get us off of doing 2 dimensions, but if I were to type into the program here what methane looks like, give me a sec. Is methane actually going to be flat? Well, I mean, right now it kind of looks flat, but you can probably tell there's a little bit of 3-dimensionalness to it. Can you see how it goes in like all 4 different directions? We call this a tetrahedral shape. And I imagine some of you already kind of played around with this. Go ahead and grab breakfast. I'm going to keep talking though. If any of you have ever started playing around with these and you have them going, say, in 4 different directions, this is like a basic tetrahedral methane kind of shape where it goes, up, out, side, and over. It's not flat, obviously, right? When you put it in 3 dimensions, it's got to go in, 3 dimensions, right? Is that pretty easy so far? You guys are still playing, obviously. Okay, here I've got a slide that then talks about how you can actually have multiple bonds. So I've already kind of showed you them a little bit here. You can have a double bond. A double bond is where you have 2 lines in between. All that means then is in that shared collective area in the middle, that communal pool of electrons, in a double bond you have 4 electrons there. In a triple bond, you could actually have as many as 6 electrons in there. Why can't you have a quadruple bond? It's actually pretty much impossible. There's only one molecule I can think of that can actually have a quadruple bond. I don't think it actually is stable. Because the only way that would work is if you somehow had a molecule where you had something, and there were 1, 2, 3, 4, all of the electrons were like shared right there and right there. And there's really no known elements that can do that. The only one I can think of is actually carbon. What carbon could do is you could have 2 carbons next to each other, and what you could have happen is this guy could form a double bond, a single bond. This guy could make it form a double bond. These guys could kind of link up and make it form a triple bond. And if you kind of were imaginative, these guys could kind of loop around and form a quadruple bond. But for the most part, that's really not possible as far as I've ever seen. So ideally what you're looking for is something like this, either a single, a double, or a triple. And as you guys play around with the molecules, hopefully you'll find a way to kind of make them fit. Triples are actually really hard to do on some of these kits here, but you might actually find one that works. So here's kind of some pictures that kind of illustrate how you might put some of those ones together. Let's say that I asked you to do carbon dioxide. The way carbon dioxide would work is you'd have an oxygen here, a carbon here, and an oxygen here. And you'd start by saying, well, let's link these guys together. But then you'd have a whole bunch of single electrons left over. So you might say, okay, well, let's have this one and this one join up, and this one and this one join up. And what ends up happening is you put a double bond here and here, and it makes it a flat across molecule of carbon dioxide. I'll make one of those real quick right here for you. This is how a carbon dioxide would look if you can kind of see it from there. You'd have a carbon in the middle and 2 oxygens on both sides. And what would have originally happened is the carbon would have linked up here with an oxygen, here with an oxygen. But what would have happened is you'd have had an extra hole right here, and an extra one over here, and then also an extra one on the bottom and one over there. So what would happen then is this guy would kind of loop back to there, and this one would loop back to there. And now you're going to have a molecule that would look something like this. In terms of its shape, it kind of looks like almost there's one that's going like in a horizontal direction, one that's going to go in a vertical direction in terms of like these bonds. But keep in mind that's not actually what they look like, because what do these things here just really represent? Yeah, 4 electrons, just somewhere in that vicinity being shared. So, okay. And you guys can see the other one here. This is cyanic acid, HCN. It's hydrogen cyanide. If I were to put all of these together and I were to ask like my 5-year-old, Kinsey, link all these guys up, the best way of doing this would be to say, well, okay, look, I'm going to link this one and that one there. And then you'd say, hang on, I've got extra electrons right here, extra electrons right here. Well, hey, why don't I link these ones together? Why don't I link these ones together? Now you end up with a triple bond, 1, 2, 3, between nitrogen and carbon. Count it up. Does everybody have enough electrons? Does this hydrogen right here have access to 2 electrons? Yeah, because isn't this bond right here made of 2 electrons? This carbon right here, does he have access to 8 electrons? Yeah, because this bond has 2. That makes it 4, 6, and 8 electrons right there. What about this nitrogen? Does it have access to 8 electrons? Well, on paper right now, it looks like there's only 2, 4, 6. But you know what I didn't draw? See that lone pair that's sitting right there? That was physically incapable of bonding? Really, there is still a lone pair of electrons still sitting on this nitrogen right here. This pair right here, which was this pair right here, it's still sitting there. It's just in calculus structural formulas, we don't usually draw them. It's kind of assumed that if there's not enough bonds to make up to 8, then the excess must be electrons. The last thing I'm going to show you in this particular lesson is that we can actually work with polyatomics in the exact same way. You guys know where the polyatomics are in your periodic table, right? That's those top section and the little gap in the table where we have things like NH4 plus or CO3 2 negative. Those are polyatomics. I can also kind of show you how to make those in this system here, but the way you draw them is a little different. Okay, what you need to do is this series of steps here. I'm not going to read all of it, but I'll give you the cliff notes. First, you got to figure the total number of valence electrons that you're allowed to have. Okay. And if there's a charge to the molecule, either add or subtract electrons. So basically, figure out how many electrons are in your pool to work with. Okay. Step 2, figure out which atom is going to be your central atom. Okay. Usually this is fairly intuitive. It's supposed to be the one that has the most unpaired electrons, but I don't even use that when I describe this to kids. When you figure out which one the central atom is, it's going to usually be the one that's like by itself. For example, in NH4+, the N will be the central atom. If I give you CO3 2-, the C will be the central atom, just because it's the one that's kind of by itself. Okay. And then step 3, you're going to add valence electrons until you make the octet rule. Okay. If you haven't used them all up properly, eventually you're going to use double and triple bonds. So let's just do an example. So let's try to do chlorate, ClO3, negative. I'm going to try to show you what a chlorate looks like. So here's the way I like to organize this. First, you got to tell me how many valence electrons does the chlorine bring to the table? Chlorine brings 1, 2, 3, 4, 5, 6, 7 valence electrons. How many valence electrons does an oxygen bring to the table? 6. But I'm going to times that by 3 to get 18 because there's 3 oxygens there. And then because there is a -1 charge, I can't spell today, you need 1 more electron. So when I sum all this up, how many total electrons do I get? 26. That makes sense? So there's step 1. Put a big 1 next to it here. Step 1, add up how many electrons you have to work with. So 7 from chlorine, 6 times 3, 4, 18 from oxygen. And then that -1 charge is super important. It gives you 1 extra electron, so we have 26. Now what we'd like to do is we want to use those 26 electrons and try to piece together a polyatomic that uses 26 electrons total, but somehow everybody still fits the octet rule. So second step here, we should figure out who's going to be your central molecule. And the central molecule is hopefully kind of logical, is that because we have 3 oxygens here but just 1 chlorine, let's start with the chlorine in the middle. He's going to go in the center. And everything's going to branch outwards and radiate outwards from there. How many electrons is chlorine going to need around it then? No, 8. Because it needs to still fit the octet rule. I know it brings 7 to the table, but it still needs 8 around it. So I'm going to start doing that. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now let's place one of our oxygens. I don't care which side I place it on, so I'm going to place it on this side over here, just randomly. How many electrons does this oxygen already have access to? Well, it already has 2 access, right? So it needs to get up to 8. So 8, this will be numbers 9, 10, 11, 12, 13, and 14. So there, I've now used 14 of my electrons, and 2 of these have been placed. Now, don't keep going in a string of things. Okay, the way these have a natural tendency to work is that they always start with 1 in the middle and they radiate outwards. So I'm going to pick my next oxygen to say go on this side right here. This chlorine is going to be like the hub. I'm also going to eventually put another oxygen, say, over here. And then I just need to keep adding electrons. So what was I up to last count? 14? 8, 9, 10, 11, 12, 13, 14. Yeah, 14. So I'm going to go 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Hey, look. It just works. Which actually it should. Because honestly, if it didn't work, we would not have it as a polyatomic on our list. Does that make sense? Like, for example, Cl2O5 negative is not a polyatomic because I can't find a way to piece this together with all of the electrons that are in play. Does that make sense? So that's why this thing doesn't exist. But hopefully you can see here, does this oxygen have 8 electrons around it? Yeah. Does this chlorine have 8 electrons around it? Does this oxygen have 8 electrons around it? Yeah, everybody has 8. So the last thing we would do then is that if this was a Lewis structure, we'd be good. That's a Lewis structure. If I asked you for the Kekulé structure, we'd probably draw it more like this. Oxygen to chlorine to oxygen down to oxygen. We put a big bracket around it, and I put a negative in the corner. That negative is super important. If we don't have that one extra electron coming from somewhere, we wouldn't have had enough. I'll say that again. If we didn't get this one extra electron right here, we'd have only had 25. And would 25 have been enough to make this molecule fit together? No. Which helps explains why ClO3 needs a negative charge. Whereas if I do another one later, if I gave you CO3, it needs 2 more electrons to fit. Otherwise, you wouldn't have enough electrons to piece it together. That makes sense? Let's try another one. Let's try nitrogen oxygen with a negative charge, as well as a nitrogen oxygen with a positive charge, so that we can try to draw what these would look like. So nitrogen brings to the table 5 electrons. Oxygen brings to the table 6 electrons. And if we're doing the one with the negative charge, I get 1 extra electron. So if I'm doing this guy right here, we have a grand total of 12 electrons to work with. Everybody good on that? All right, let's start piecing them together. Really, there is no central molecule. There's only 2 of them here. I mean, it's going to be nitrogen. Let's say he's going to use 1, 2, 3, 4, 5, 6, 7, 8. And then you'll put next to it an oxygen. This will be 9, 10, 11, 12. Uh-oh. What's wrong? I've used all my electrons, right? But did everybody get 8? Okay, well, we can be clever. We can find a way around this. What if I were to redistribute them slightly? What if these ones weren't just nitrogens, but what if those 2 electrons down there were also in the communal pool of electrons in the middle? Do I still have 12 electrons? Yeah, 1, 2, 3, 4, 5, 6, 7, 8. I've got some that are exclusively for nitrogen. These 2 are just nitrogens. These 2 are just nitrogens. These 2 are just oxygens. These 2 are just oxygens. Okay, so that took care of 8. But then 9, 10, and 11, 12, those are the bonds between them. So if I were to ask you what a nitrogen and oxygen with just a single negative is as a polyatomic, it is N double bonded to O, but it needs 1 extra electron to occur. There, I've now made a valid polyatomic. Is NO negative one that's on your list, though? I don't believe so, but if you knew how to name them right, you know how NO3 is a nitrate? NO2 would be a nitrite. NO negative then would be a hyponitrite. So this thing is actually a valid polyatomic. It's called a hyponitrite. Now here's one that you haven't seen, because I don't think this one's on your table, an NO positive. Is an NO positive possibly a thing that could work? Well, let's try to piece it together. So same logic as before. Nitrogen brings 5 to the table. Oxygen brings 6 to the table, but hang on, you have a positive charge. What does that mean? Come back, come on, you can do it. No, it's going in a circle. Okay. If you have a positive charge, what does that mean? Do you need one more electron? You need one less electron. So we were supposed to have 11, but if we're having one less to the positive charge, we need only 10 electrons now. This is going to make it more challenging. I'm going to have nitrogen and oxygen here. Let's start giving them electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bah. Oxygen doesn't nearly have enough. Hang on. Any ideas? Yeah. Take these two right here and those two right here and say, why don't we shove them all in the middle? So I'm going to go with another one here, another one there, another one there. So now nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 in its sphere of things. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8 in its sphere of things. 6 of them are collectively in the middle. We call that a triple bond. And so if I were to write this one out, N to O with a positive charge is actually a possible polyatomic. It's not one you guys are expected to know, but it is one that actually could exist. That would be the way you'd make it, though, yeah. So, this is one of the cool things about this section here is that really you're only limited by your imagination. This is why I like giving you guys the blocks to play with, because most of you have already started to come up with, well, what if I do this and this, and you've got these cool elaborate structures, right? If you can make it fit, it could be a stable molecule. There are other factors in play than just that you can make it once. Like, for example, some molecules do not have the ability to stay, and they chemically decompose. You guys know how we have formation, decomposition, single replacement, double replacement. There are some chemicals that will just naturally decompose. And so if I were to give you, for example, like say NOCl, this might be a logical molecule. The NO is a positive. The Cl is a negative. But this might naturally just decompose into nitrogen gas, oxygen gas, and chlorine gas. So even though I can build this on paper, it might not actually be stable, and this might occur instead. But I mean, maybe it's only stable for like a millisecond. You know what I mean? In the same way that you guys know about half-life for some equations, for some things, where like it's stable for like 0.7 seconds and it decays. So just because you can make it doesn't mean it's actually going to stay that way. Wait, can I hop right into the next set here? Because what I'd like to do now is transfer from flat two-dimensional drawings to where you guys are at now, where you're playing with these molecule kits. I want to talk about the different shapes you can have and how these guys look in 3D. So can I just do, let's say, one more of these ones here? Because this is really a review from last day, and then we'll move on. Why don't we do pH3? How would pH3 look if I had to draw it? So step one, phosphorus, we need to figure out what it looks like. Phosphorus has 1, 2, 3, 4, 5 valence electrons. So 1, 2, 3, 4, 5, I guess. I don't really care which one doubles up. Each hydrogen is going to go like, say, there, and there, which means when you're done, you're going to have this molecule, P to H to H to H. The other side of the phosphorus, it implies that you have a valence pair just kind of sitting there. So here's what it would look like. Here's what you'd have. It's going to go in 4 directions. 1, 2, 3, 4 directions. 3 of the sides are going to have a hydrogen on them. And the remaining side is going to have that lone pair of electrons. Somewhere in there is some electrons. They need space too. They count. They're people. Well, they're electrons, I guess. So don't forget about lone pairs. They count. Any issues with that so far? All right, moving on. Um, Before I get to that part, though, I want to talk first about ionic compounds again. Everything I've been focusing on recently has been covalent compounds. And the reason why they're covalent compounds is because those bonds that we're drawing with a little stick, those are shared electrons. When you guys are making all of your cool molecules here, those sticks are shared electrons that are in between things. But ionic compounds work a bit differently. Ionic compounds are held together. The word we're going to use is electrostatically. Okay? And I'm going to use some of these little pieces here to help try to illustrate this. So you guys can see. I'm going to do this, though. Actually, you know what? I'm going to do it at the back of the classroom here, and I'm going to steal some of yours, Hudson, because you're a really nice set of all these ones here. So let's steal some of these. Hopefully you guys can roughly see with where we're at. Okay. Imagine that this right here is sodium, and this right here is chlorine. Okay. Do we need to put a bond between them? Do we need a bond between the sodium and the chlorine in the same way? The answer is no. Because what does this bond right here represent? Shared electrons. This is the overlap of orbitals where there's 2 electrons found in there. But does a sodium and a chlorine actually share electrons? No. Chlorine's a thief. He's a bully. He stole all of this guy's electrons. Sodium had an electron, and chlorine has taken it. So this guy is now positive, and this guy is now negative. Well, what ends up happening is this keeps happening over and over again. So, well, then, same thing happens here. This guy was sodium, this one's a chlorine. This guy steals his electron. This guy's positive and negative. And what you can then make is this interlacing pattern, which we call a crystal lattice. See that? See what I'm doing from where you're at? Oh, these things are rolling everywhere. What ends up happening is you have a pattern here where then it goes positive, negative, positive, negative, positive, negative, positive, negative, rolling off the table. But hopefully you get the point. That's kind of what that picture right there is supposed to show. So hopefully, I don't know if that was useful or not. Let me go up to here. Here's kind of the idea. We don't need to put a stick in between them because the stick represents shared electrons. These guys aren't sharing their electrons. You're positive, you're negative, you're positive, you're negative, you're positive, you're negative, you're positive, you're negative. Does that make sense? And because of that, in 3 dimensions, they just build together. Anybody ever seen those little magnet balls that sometimes you can get that stick together? I think of that like this here, where it's going to keep growing and growing and growing. Well, this helps explain why most things that are ionic are solid. Does that make sense? Because I can just keep growing this thing bigger and bigger and bigger and bigger, and it gives it a solid sort of feel to it. Okay? So the first thing I need you guys to know is that if we're ever talking about ionic compounds, all of the following rules don't even apply. Because ionic compounds bond completely differently. They bond electrostatically. That's the word we're going to use, electrostatically. Where you basically get this pattern of positive, negative, positive, negative, positive, negative, just over and over again. Now, here's one of the weird things about it, though, is that although we might write the formula as NaCl, that may not actually be true. Because is there just one sodium and one chlorine right here? No. There's probably 500 sodiums and 500 chlorines. And so what we're actually doing when we write the formula NaCl is we're reducing it. Rather than writing it as Na500, Cl500, we're reducing it to lowest terms and saying, well, there's one of each, basically. Does that make sense? If I only looked at this section right here, there's an NaCl. Here's another NaCl. Here's another NaCl. But they keep growing together as a crystal. Does that make sense? So the term we use is an empirical formula. I've got that on a future slide, but this right here is known as an empirical formula, CaCl2. Is there ever going to only be 1 calcium and 2 chlorines, though? No. It's probably going to be more like calcium 1,000, chlorine 2,000 is what you're really going to have. You get what I'm saying here? Based on the way that you're going to have so many of them all bonded together. So electrostatically is the word we use for ionic things. If we want to describe its shape, the shape we use is called a crystal lattice, where you have this interlocking shape of positive, negative, positive, negative, negative, positive, negative, positive. Okay. Now, these things, although they are solid, there is one problem with them. They're very brittle. When I was trying to make the molecules over there next to Sam and Hudson there, I couldn't even get them to stay next to each other. They were rolling all over the place. That same problem kind of still happens at the molecular level, is that you can break these things. If you were to drop this, it would like cleave in half and fall apart a little bit. So although they are in a solid format, they're not necessarily the strongest thing we actually know. How do you break an ionic bond? Add it to, yeah, I mean, water can dissociate it. So even though it's in a solid format, though, it is very breakable, okay? We're not talking indestructible by any means here. But we are talking a solid phase of matter because they stick together quite nicely. So that's what I have on this slide right here. The word I need you guys to know is it's called an empirical formula. Okay? We don't write how many you actually have. What we do is we write it in lowest terms. So we figure out what the ratio should be. So like 2 to 1 or 3 to 1 or 1 to 1. Okay? But truth is, in real life, you actually have way more than that. Okay? Most of the time, when I'm going to show you a picture, I'm going to show you a very basic one. I'm going to show you a picture like this where there's NaC or NaCl, NaCl, NaCl. I'm just going to give a nice 1-to-1 ratio. But if you were to have a compound like CaCl2, they can actually have some really cool shapes. Like this right here is what the lattice would look like if you had a 1-to-2 ratio, where there's like, say, 2 of these guys for every one of those, and 2 of these guys for every one of those, and 2 of these guys for every one of those. And you can get some pretty cool different patterns actually that occur. But at the end of the day, there's actually not actually a line in between those ones there, because the line usually represents sharing of electrons, and we're not even sharing electrons. We're literally giving and taking them away. We just like the line here because it helps us to visualize it a bit better. Okay, moving on. What I want to focus on today then is not the ionic stuff, but what you're building here, the molecular stuff, where you have those shared electrons in the middle. Okay. The word I need you to know here is they are held together by intermolecular forces. Okay. I'm going to steal some molecules here since you guys have pre-made them. Sam, can I take one of each of yours there? I'll try not to break them. Do my best. Okay, so the boys here have actually been quite clever. I like these guys. Well done here. So I need to show you vocabulary. This thing right here is one molecule. Here's a different molecule. If these things stick together, and then other ones stick together, that would make it go from gas to liquid to solid. Does that make sense? What makes this molecule here and this molecule attract each other is going to be known as an intermolecular force. Okay. These bonds inside here are known as intramolecular forces. Okay. This is a bond within the molecule, so it's known as an intramolecular bond. Okay. It's what keeps these two pieces together. It's what keeps these two pieces together. It's what keeps these two pieces together. Okay. So any of these things right here are called intramolecular bonds. But if you want this guy and this guy and this guy to start clumping together, is there actually physically a black stick between them, kind of keeping them together? Well, no. But if they do start to group together, then they'd start to become, say, liquids or solids. Okay. What keeps these guys together then is called an intermolecular bond. Intra, inter. Does that make sense? So that's the vocabulary we're going to use here. Did I give those back to other people? Keep playing. And so what I need you guys to know is that most covalent compounds are either a liquid or a gas. Most of them are liquids and gases. Our goal eventually is to try to explain why some are liquids versus some are gases versus why some are even solids. Okay? And so I've got to show you some different shapes. Since you guys have been playing for a good part of the last hour here, you'll start to recognize a few you've seen. Like, for example, here's a really common shape where you basically just have it go flat across. Thanks. This is known as a linear shape. There's also one here known as like an angular shape or a tetrahedral. What we want to do now is move our way from drawing these in flat 2 dimensions to being able to visualize them in 3 dimensions as well. So, okay, what I've got on the next few slides here then is a whole bunch of different ways that we can represent molecules. So here's the first one. I can give you an empirical formula. The way the empirical formula works is that it's always reduced to lowest terms. So I've got C6H12O6. The empirical formula for this then would be CH2O. Can you guys kind of see how I got that? Rather than having 6, 12, and 6, I'm downscaling it to the lowest possible numbers. Just like I did with the ionic compounds before. Rather than having 1,000 and 1,000, I said 1 and 1. Rather than having 6, 12, and 6, divide each of these by 6, and 6 divided by 6 gives you 1. 12 divided by 6 gives you 2. 6 divided by 6 gives you 1. Does that make sense? So that's an empirical formula where you're basically reducing it to lowest terms. We rarely use these, though. We do, but it's not all that common. Usually we don't use that as a good way of trying to describe things. I found this slide on the internet. I thought this was kind of silly. If you have 2 hands, really in a way you could say that you have H2F10. You have 2 hands with 10 fingers. Okay. A 3-handed alien, silly, but a 3-handed alien has 3 hands and 15 fingers. But at the end of the day, the empirical formula is still the same. For every 1 hand, you have 5 fingers. That's all you're doing, is you're just reducing it to lowest terms. Okay. Here's another way that we represent molecules. This is the one that you guys would have learned at first. A molecular formula. When we write it like this, like say H2O2 or H2O or C2H6, those are molecular formulas where we write out everything that you have. The empirical formula then is just where you like cut it in half. So see how there's H2O2 right here? If you use an empirical formula, you just have H and O. Here, water, by the way, water's molecular formula is its empirical formula because you can't cut it in half at all. Okay? But this is mostly what we use, is the molecular formula. Okay? Then these are the ones I've just shown you more recently. Rather than writing it out like CH3COOH, sometimes we want to draw it like this. Okay? Do you guys remember what CH3COOH is called? We did it recently in a lab. This is acetic acid. This was vinegar. Anybody ever wonder why we write CH3COO in such a funny way? Like, why do we write it as CH3COO? Why don't we write it as C2H3O2? Well, now look at the way I've drawn it. I've now pieced together its Lewis dot formula. Check this out. You've got C, H3, C, O, OH. Can you see that? Sometimes the way we write it like this is written in such a way that it makes it easier for us to know how it's been pieced together. Let me do that one more time here. If you ever wondered, why do we write it as CH3COO? Why do we write acetate like that? Why don't we write it as C2H3O2 and then throw an H on the end? Well, the reason why is this. Here's 1 carbon. Then there's 3 hydrogens around it. Then there's 1 carbon. Then it branches to 1 oxygen that way, 1 oxygen that way, and then to the hydrogen. If it went like this, by the way, if it went C to H to H to H to C to O to O to H, I bet you would have written it as CH3 CO2H because those 2 O's are like next to each other. So sometimes these formulas give you a clue as to how they're written. Structural formulas then is what I also showed you earlier in the previous lesson here, where all you do is you take the electrons out and write a bond line in between. Here's my goal now, though. I want to show you how to draw what's called a stereochemical formula, which is basically we need to find a way to draw in 3 dimensions on paper. Okay, and there's a technique we use because you guys have now been playing for like an hour. Hopefully, you guys kind of realize here that we need to be able to show a 3-dimensional rendering somehow. So here's how this works. If you were to have a molecule, I'm going to make one real quick here, like this. Stand in front of the board here. Okay. Here's a very typical molecule. It's called a tetrahedral shape. There's a central molecule that goes off in 4 directions. Okay. If I want to try to draw this on paper, I draw it like this. Okay. So you guys can see this. I'm going to hold it flat like this. This line right here that goes up to the top chlorine is going up. Okay. This one right here that goes towards my body a little bit is going down like that. Then these 2 lines right here, this and this are notations, the wedge and the dash line, to describe coming out of the page and going into the page. You ever see dashed lines like this? It implies a molecule that's kind of going into the plane of the paper. If you ever see like a solid line like this, it's coming out. So I'm going to hold this up again. Hopefully you can kind of see this. This one's going up. This one's coming down to the side right there. This one right here the one that's coming slightly towards you, like going mostly towards Chelsea there, that would be this one right here, this wedged one right here. And then the one that's going kind of in towards the screen, this back one right here, it's that guy right there. And so this is our way of drawing what's called a stereochemical formula, where we're drawing in on flat paper in 2 dimensions. We're trying to represent what 3 dimensions actually would look like. So I'm going to put a little note here. This is coming out of the plane, and this is going into the plane. Do you guys get what I'm saying when I mean out of the plane and into the plane? So this is flush, this is flush, this is going... Anyways. So when you guys play with these little model kits, then you have to be able to recognize when we're drawing them, do we need to draw something where it goes in or out or up or down? Like, how do we represent that? So we're going to do the exact same task we did earlier in the class, only now rather than drawing them flat, we're going to try to draw them in 3D. When it comes up, because I do have this on one of my labs, I believe, and it's also on a test, it's called VSEPR theory, VSEPR. It's an acronym. It stands for this: valence shell electron pair repulsion theory. I want to take that one word at a time and describe it. Valence. What are our valence? What does that mean? Just the outside electrons, yeah. So it's the outer shell electrons, so only the outside shell electrons. Now they always come in a pair. Remember how we talked about the bond is always 2 shared electrons? Or the lone pair is also a group of 2 electrons? That's that whole quantum theory of entangled particles, but they always come in a pair. Here's the important part. They want to repel each other as much as they can. Do electrons want to be by other electrons? No. It's actually kind of weird. Electrons are okay being next to one other electron. They're okay being by each other in a pair. So like that bond that we made, you know, this little bond that you've got right there, there's 2 electrons in there. They're okay being relatively close to each other. But they want the other pairs of electrons as far apart as possible. And it leads to some cool geometric shapes. Here are some of the shapes we're going to have. Okay. Let me try modeling them with the models we have here first. The first one is very basic. It's linear. If you have a linear shape, it literally is flat across. This is a good example of a linear molecule if you've ever made one of those. Or, I did one of these earlier, so let me try it again here. Something like this would also be linear. Can you guys see how it's just flat across? Just a straight line. That's linear. Trigonal planar would be something like this. Now, it's a little awkward because there's 2 bonds right here, but when you look at it from a second here, you see how it goes down, out, and over? Is there any, like, I know it's not going to lay flat because of the curved surface, but do you see how it kind of basically lays flat in my hand? It's in a complete plane, and it's going in 1, 2, 3 directions. Often these occur because you actually have a double bond sitting in here. This is a trigonal planar. Okay. The next one is tetrahedral. Tetrahedral is where you have a very similar one, only you go in 4 directions. I've already shown you one of these before. This is your basic tetrahedral. You're going to go off in 1, 2, 3, 4 directions. Okay. Trigonal pyramidal looks like this. You're only going to go off in 3 directions. But see how this one's not flat? It's almost like a tripod. Okay. The reason why it's not flat is that there's a lone pair on this one. Okay. I want to show you both of these side to side here so you can see the difference. Okay, this one right here has 3 bonds. 1, 2, 3 bonds. Okay. But this one sits flat. That makes sense? This one here also has 3 bonds. 1, 2, 3 bonds. The difference here is that this guy has a lone pair. And lone pairs still count. And so what ends up happening is it's almost like the tetrahedral. The tetrahedral would have been the exact same type. It would have gone in 4 directions like this. Only rather than there being a bond here, you put a lone pair there. It has 3 different sides to it, but now it's more like a tripod. That's another shape you can have. And then the final one you can have is the V-shaped one. This is what water does, actually, where you just get like a V out of it. Okay? And the reason why it's not flat across is because you've got lone pairs in these spots here. Depending on the type of bonds you have, depends on whether these things are going to be more like to be solids or liquids or gases. So that's my last goal. We're going to try to draw some of these. So, This, by the way, is a very useful slide. I had some kids in the past actually literally cut this out of their notes and paste it into their data booklets because they found this one useful for being able to figure out different shapes. So if you want to do that later, by the way, feel free. But let's try some examples here. Let's try to figure out the shape of SO4 2-. Let's figure out what kind of shape it's going to have. So first thing we got to deal with then, we got to draw it just like we did earlier. How do you draw something with a 2 negative charge? What's the mechanism for this again? Count up all the electrons. So sulfur gives us 6 electrons. Oxygen gives us 6 electrons, but we need 4 of them, so that's 24. And then there's a 2 negative charge, so that gives us 2 more electrons. Grand total, when we're done, how many electrons do we need? 32. That's step 1. That makes sense? Step 2, who's going to be the middle of this molecule? Sulfur? Does that make sense? So let's put sulfur in the middle and start giving it electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's put an oxygen somewhere. 9, 10, 11, 12, 13, 14. Put another one on here. What was that, 14? 15, 16, 17, 18, 19, 20. I need another oxygen. What was that, 20? 21, 22, 23, 24, 25, 26. I need a fourth oxygen. 27, 28, 29, 30, 31, 32. Actually, that worked perfectly, didn't it? But I mean, shouldn't it? It's not SO4 1-, it's SO4 2-. You ever wonder why some things have a 1 negative charge and other ones have a 2 negative charge? This is why. In order to piece it together, the only way it pieces together is that SO4 needs 2 extra electrons. So here, this would be that guy there. Now here's my question then. What sort of shape is this going to have? If I were to draw this in 3 dimensions, what would it look like? Well, it would look like this. You're going to want a sulfur going up to an oxygen, over to an oxygen, into the page to an oxygen, and out of the page to an oxygen. This is going to have that tetrahedral shape. Can you guys kind of visualize that? This needs to go in 4 directions. So when it goes in 4 directions, its electrons want to spread out as much as it possibly can. And so, I mean, most of the bonds that Daniel's looking at there and that thing right there are probably all tetrahedral, where they go like this way, that way, this way, this way. They're going 4 completely opposite directions. We call that a tetrahedral shape. And this is how we would draw it on paper. Just want to see if this will work. Oh, never mind. This isn't going to work. Ah, there we go. Ignore the double bonds. Can you guys see how this has that tetrahedral shape to it, though? How, if I were to line it up here, let's say I can line it up here. There we go. This is going up. This is going down to the corner. This one is coming out of the page at us. And then that one is going into the page. That's what we just do right here. Up, over, out of the page, into the page. Let's try another one. Let's try to predict the shape of ClO3-. We actually did this one earlier. We did this one earlier today. ClO3- was chlorine needs 7 electrons. Oxygen needs 6, but we need 3 of them. So that's 18. And then we need 1 extra electron. So that's 26 total. Alright, let's start. We did this one earlier. Chlorine gets 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. This is what we drew just like 20 minutes ago. How is this one different? has a lone pair. Rather than having somebody up top here, it has a lone pair. But this functions almost the exact same way. Again, let me make one of these again for you. If you can see this from where you're at. This is what it looks like, roughly, if it's tetrahedral. It goes in just 4 different directions, right? Pull one off, put a lone pair in its spot, and now it's got that pyramid shape to it. And I'm going to try to draw that now for us as to what it would look like. Okay. I'm going to draw it like this. I'm going to put the chlorine right here. I'm going to go down in the corner right here to one of the oxygens. I'm going to go into the page over here with a second oxygen. I'm going to come out of the page with a third oxygen. And then the top is that lone pair right there. And this is what a chlorate should look like, hopefully. It would have, the shape we would call it would be a trigonal pyramid. Trigonal because it goes in 3 directions, at least for bonding. But it has a bit of a pyramid shape to it. Can you guys visualize the pyramid part of it? How much time do I have here? Pushing it. Okay, let's try another one. C2H4. This one's a bit more challenging because there's not just one carbon in the middle, there's 2 in the middle. I'm going to show you how to do that in a second here. Let's piece it together though. This one's different though because it's not an ion. We're now back to using Lego shapes. So I'm going to draw a carbon. I'm going to draw a second carbon. And then I'm going to draw 4 hydrogens to go with it. Okay, we got to find a way to piece them together so that everybody gets 8 electrons. Well, except the hydrogens. Hydrogens get 2. Okay. Now, more and more experience will tell you what the best way of doing this is, but the best way to start, honestly, is just to combine the 2 carbons together. Right, let's put the 2 carbons together like this, and then work from there. Now, there's supposed to be 4 hydrogens, right? So, I guess why don't I put 1 hydrogen right here? Maybe let's go 1 on the opposite side. Why don't I put another hydrogen right here? We'll put another one on the opposite side. I think I've now used everybody up, though. I went through that a little bit faster than I'd like to, but that makes sense. Like I started piecing things together. I linked these guys. I added a hydrogen here and here and here and here. I just picked them randomly. Is everybody filled up, though? What's wrong? No, there's extra, what do we call these guys? Bonding electrons. There's extra bonding electrons. How can I solve this problem, though? Yeah, make it a double bond. There. Move this, get rid of this one, get rid of this one, make it a double bond. Here's what's going to happen on this one here, then. I'm going to, now that I've done this one here, this is called ethene. I just happen to know its name. I'm going to show you it on the molecule maker here. And then you'll be able to see what it looks like in 3D. I think I might have to call it a day after this, though. This was ethene. Ethene looks like this. Okay. I want to go back to what we just drew here. We had a double bond in the middle. We had 2 hydrogens off one carbon, 2 hydrogens off the other carbon. Now look at this guy here. I've got a double bond in the middle, 2 hydrogens. But what's happened here is I have trigonal planar shape. Okay? You see how this guy's completely flat? The reason why is that this guy right here is going in 3 directions. I know this is a double bond, but it's going in 3 flat directions. And this guy right here is also going in 3 directions, but also flat. What ends up happening on this one, if you can make one along, is it looks like this when you're done. You guys see how there's a double bond right here in the middle, and then it goes 1, 2, 3 directions there, 1, 2, 3 directions there, but essentially it's a flat shape. Right? The reason why is that unlike the other one, where it had to build a bit of a pyramid to it, build the pyramid, see how this one went in 3 directions as well, but the 4th direction was a lone pair. This one right here goes in 1, 2, 3 directions, right? But rather than the 4th direction being a lone pair, it doubled up on the bond. So we end up getting is what's called trigonal planar. This is still in 3 directions, but it's flat. Okay? So when I want to draw this one then, I can actually draw this one in a flat shape then. I don't actually need 3 dimensions, so I can draw it like this. Carbon to carbon, up to hydrogen, down to hydrogen, up there, right there. And what you end up having then is two central molecules. This one right here and this one right here are both known as trigonal planar. Last thing that I'm going to call it a day here. We can actually start building then more and more complex molecules, because that's what you guys have started doing, obviously, right? So I'm going to show you one last one. I'm going to show you methanol. Here's methanol. I want you to look at the shape of methanol here. Can someone tell me what the shape around the red atom is? Of the 5 we learned. I actually haven't done it yet. Do you guys remember the name of one of the other shapes? Bent. Yeah. Can you guys see how this guy right here has just that bent shape to it right here? Whereas this one right here, around this guy right here, it would be tetrahedral because it's going in 1, 2, 3, 4 directions. As we get into bigger and bigger molecules, you're going to have lots of different shapes there. Let's finish with this, I guess. Oh, that didn't work. Here, if I were to give you a really crazy one, this is Tylenol. Take a look at Tylenol right here. Right here, this is a tetrahedral shape, 1, 2, 3, 4 directions. This guy right here has a trigonal planar shape. If you can see it, this piece right here is completely flat right there. This guy right here, around the blue one, is also a trigonal planar shape. It's perfectly flat. This thing right here up in the corner right there, though, that's got a bent shape to it. As these molecules get bigger and bigger and more complex, you get lots of different shapes to them. So, anyways, I think I've hopefully covered what I wanted today. My main goal, do you guys think you can now draw and make molecules in 3 dimensions a bit better? Okay. You're going to want to practice this, obviously, but I'm out of time, so we'll do more tomorrow.